All right, today we're going to be looking at conic sections in the form of degenerate conics. So what we know of a conic section so far is that we take a double napped cone and we slice a double napped cone with a plane. And when we slice it with the plane, we're able to make the four conics that we've been studying: circles, ellipses, parabolas, and hyperbolas. So let's take a look and see what happens when we get these degenerate. So degenerate meaning that there are going to be some special cases of slicing the double napped cone with the plane. So thinking about that double napped cone, let's take a look and watch a part of this video here to see the visual of how we can create a conic of the degenerate forms.
Degenerate conics. If the plane intersects the double wide circular cone at its vertex, the ellipse becomes a point. The parabola becomes a line, and the hyperbola becomes two intersecting lines. The figures so obtained are called degenerate conics. In this module,
All right, so that's where they come from, and we can see that depending on how we slice that double napped cone, we'll be able to form the three degenerate conics that you just saw. All right, so if you look here on this note sheet, we have 5 degenerate conics. So one that we did not see here was the empty set. So the empty set obviously is impossible. So when we have an equation that actually doesn't make sense, we end up with the empty set. We have a point. A point was found in this first example here when we're slicing the double napped cone horizontal perpendicular to the axis of the double napped cone. That's going to be an ellipse. If we slant it that's going to be a circle. If we slant it just slightly, then it would make an ellipse. But when that plane intersects the two vertices of where the double napped cone come together, we simply get a point. And so that's the second one, which is going to be from a circle or an ellipse there. The third one that we have is going to be a line. And that line comes from a parabola. So a parabola says that you're going to slice the cone so that it is parallel to the slant of the cone. And usually that would only intersect one of the cones, not both, which just makes a parabola. If the slant is equal to the plane and that plane is tangent to both cones, that's going to make one single line. The fourth one is 2 parallel lines, which is also a parabola. Now this one is a little bit obscure. If you read about it, this is kind of a degenerate of a degenerate. Thinking about a double napped cone could essentially, if we take our double napped cone like so, and then we think about those vertices coming apart and it kind of becomes more cylindrical and more cylindrical, more cylindrical until it does become a cylinder. And then we take this cylinder here and we slice this cylinder with the plane. We're going to end up with just 2 parallel lines on the outside of that. So it's sort of a degenerate of a degenerate. And then the last one is 2 intersecting lines, which comes from a hyperbola. So a hyperbola is going to be slicing the cone parallel to the axis. And so when we do that here, if we pass through the vertices, then we are going to end up with 2 intersecting lines. So you can notice that each of these degenerates results from a plane passing through the vertex of both cones. All right, so now let's see what that means for identifying these degenerates. So one way that we can identify the degenerates is to use the discriminant. So if we remember, the discriminant, just like it was from the quadratic formula, is going to be b squared minus 4ac. So we want to use this to identify the following conics. And we've done this before. So we're looking at our b squared minus 4ac. In this case, we have a 1 in front of the x squared, a 1 in front of the y squared, and a 1 in front of the xy. So this is our a, this is our b, this is our c. So if we calculate that b squared minus 4ac, I have 1 squared minus 4 times 1 times 1. And I calculate that, and I get 1 minus 4, which is negative 3. So I'm going to label this D. So my discriminant is equal to -3. And based on that information, I know that I'm going to have either an ellipse or I'm going to have a circle. And then I could complete the square and I could identify further which one I'm going to have by actually solving this one a little bit more. But with the discriminant, that's what I have. Next, I want to identify the number 2. So number 2, again, my a is the coefficient of the x squared, the b here is the coefficient of the xy, and the c is the coefficient of the y squared. So my discriminant is equal to 2 squared minus 4 times 1 times 1. So I get my discriminant is 4 minus 4, which is 0. And based on what you guys learned previously, if the discriminant equals 0, we know that it is a parabola. So go ahead and pause the video if you want and go ahead and solve number 3 and identify what conic you will have for number 3 based on the discriminant. All right, so what you should have identified is that the discriminant is equal to 21. And since the discriminant is greater than 0, we know that this will be a hyperbola. All right, so that's just identifying with the discriminant again, and these could be degenerate conics. So let's move on to 4 through 8. So 4 through 8, it says to express in standard form and completely identify the following degenerate conics. So completely identify means that we are going to identify all the way. So if we get a discriminant that's less than 0 and we know that it is an ellipse or a circle, we need to continue to identify and figure out whether it's an ellipse or whether it's a circle. So let's go ahead and start with number 4 by calculating the discriminant. So on number 4 here, calculate the b squared minus 4ac. You should get that the discriminant is equal to 36. Since the discriminant is greater than 0, that identifies this as a hyperbola. All right, so now since it's a hyperbola, I'm already telling you here that these are degenerate conics. Whoops, that's not a highlighter. And so since you know that it's a degenerate conic, let's go back up to the top real quick. For a hyperbola, a degenerate hyperbola, we can see in number 5 here, that a degenerate hyperbola is going to be 2 intersecting lines. So now my goal is to take this equation from number 4 and determine the 2 intersecting lines equations. All right, so to do that, I'm thinking about a line. I know that a line needs to be in the form of y equals. So I can identify my y here. I see here I have y. Oh my gosh, not a highlighter again. Identify y right here. I want to isolate y, and I have y right there. So I'm going to have to somehow factor so that I get y by itself to be able to isolate y and solve for y. So let's move the x's over to the right-hand side. Start with simplifying a little bit. All right, so if I move the x's over to the right-hand side, and then I could factor out my negative with the y's, I'll do that in 2 steps. So negative y squared plus 2y minus 1, I'm going to keep that there because I know what's going to happen, is equal to negative 9x squared. And then if I factor the negative out of that so it's easier to work with, I get negative quantity y squared minus 2y plus 1 is equal to 9x squared. Oops, negative 9x squared. Then I'm going to divide everything by a negative, so I get y squared minus 2y plus 1, which I can factor to become y minus 1, quantity squared, is equal to positive 9x squared, dividing everything by a negative. And so now I can isolate the y because I can take the square root on both sides. When I take the square root here, it cancels the square. When I take the square root there, I can simplify. And don't forget, when you do square root, you have to do plus or minus. So now I have y minus 1 equals plus or minus the square root of 9 is 3. The square root of x squared is simply x. And so now this is going to be 2 equations because I have my plus or minus. So that means I'm going to get one equation is y equals, if I take the positive 3x plus 1, or y equals negative 3x plus 1. And so I've identified that I have a hyperbola. These are the equations that I end up with in the end, and these 2 equations represent 2 intersecting lines. So 2 intersecting lines. Okay. And so now we've completely identified it. We've identified it not only as a degenerate hyperbola, but the degenerate type that it is two intersecting lines. All right, let's go on to number 5. So number 5, go ahead first and calculate your discriminant and determine whether it is going to be a circle, an ellipse, a parabola, or a hyperbola. So we calculated that our discriminant is -4. Since my discriminant is -4, then I know that my equation is going to be either a circle or an ellipse. So I'm not sure which one right now, but I'm going to continue on and then I'm going to determine in the end which one I have. So if I go back up to a circle or ellipse, you can see here that a circle or an ellipse is going to be a point, okay? So a point is what I'm looking for. All right. So I'm looking for a point. Keep that in mind because that's going to help you identify what you're going to do for the equations, okay? So this one's kind of set up nicely because I have all the x's right here, and I'm going to group those together. And then I have all the y's, and I'm going to group those together. The reason why I did that is because I can factor out those x's. That's a perfect square. So for the x terms, I end up with x minus 5 quantity squared. For the y terms, I end up with y plus 3 quantity squared, and that's equal to 0. Now I have 2 perfect squares is equal to 0. So I want to think about what has to be true here in order to get a point. Again, I'm looking for one single point. I'm going to write that down at the end. I'm going to say I want a point. So a point is a coordinate. So I need one specific x and one specific y that go together to make this true. All right. So in order to make this equal 0, I know that the only way to add 2 numbers to get 0 is if you add a number and its opposite, or if you add 0 plus 0. But since both of these are squareds, so this is a quantity squared, and this is a quantity squared, each of those is either positive or 0. So each of these quantities is positive or it is 0. Well, 2 positives can't make 0, and a positive plus a 0 cannot make 0. So the only way to make this equal 0 is if both of these are 0. So what I need to have then is I need to have x minus 5 has to equal 0, and y plus 3 has to equal 0. So solving each one, I get x equals 5, and I get y equals -3, and that's my point. My point is going to be 5, -3. And so that's my final answer. So I have a point, 5, -3, but I still have to identify if it's a circle or an ellipse. So if I go back up to this line right here, I can look right there. I have no coefficients in front of my x minus 5 quantity squared term and my y plus 3 quantity squared term, so that means it's going to be a circle. Okay, because I have no coefficients, or if the coefficients would be the same. I don't have no coefficients, I have a coefficient of 1. All right, so let's continue on to 6 and 7. And I'm gonna let you guys give these ones a try and see how you do on them. So go ahead and pause the video and try number 6 and number 7 and see if you can figure out how to solve each of these problems. So go ahead and pause the video now, and then I will give the solutions momentarily. All right, welcome back. Let's see how you did. So first of all, on number 6, we want to identify what we're going to start with. So based on the discriminant, we identified that we're going to start with an ellipse. Okay, so we have an ellipse, and I know that the discriminant tells you ellipse or circle, but looking at this one, I know that it's an ellipse because of the coefficients. So there's no bxy term. So the b term is missing, so I can just look at here. I have a coefficient of 1, and here I have a coefficient of 3. So they're both positive, right? The coefficients of the squared terms are both the same sign. It means it's going to be an ellipse. So since it's an ellipse, then I know that, going back up to the top here, with an ellipse, I know that's going to be a point, okay? So I'm looking for a point. So again, I want to find any value that's going to give me the point to make the solution work. So I'm going to, again, group my x's and group my y's. So grouping my x's here and grouping my y's there. I'm going to want to factor out the 3 from the y's Actually, I'm going to move that 13 over because that doesn't help me. I don't want to factor 3 out of 13. I'll move the 13 to the other side. The x's I'm going to group with the 1 because that factors exactly into x plus 1 quantity squared. And then I do the complete the square with the y terms, and I end up with this equation. So I get x plus 1 quantity squared plus 3 times the quantity y minus 2 squared equals -1. Well, this is my problem. It equals -1. How can I have two positive numbers, since they're both squared, this is squared and this is squared, two positive numbers equal a negative number? That doesn't work. So there's no way that this is possible. Therefore, my final answer, although it was going to be a point, ends up being the empty set. So it was a degenerate ellipse, but then it actually turned into an impossible equation, so it's the empty set. All right, number 7, the parabola. Whoops, didn't mean to say it was a parabola yet, but it is a parabola. So using the discriminant, again, you identify that it's a parabola. So you're looking for either two intersecting lines or two parallel lines. So we want to solve for y. So I can see that if I group these first 3 together, these first 3, that's a perfect square. That becomes 3x plus y quantity squared. So then I move the 16 to the right-hand side, so 3x plus y quantity squared equals 16. And then once I have that, then I'm going to finish solving it for y. So I take the square root on both sides, I get 3x plus y equals plus or minus 4. And then completely solving, I end up with these two lines that are parallel. We can see that they're parallel because we can see that they have the same slope. -3 is a slope, -3 is a slope, and they both have different y-intercepts. So we have a parabola that is two intersecting lines, and we have our two equations to identify those intersecting lines. All right, that's all today for Degenerate Conics. Please let me know if you have any questions.